Hello everyone, today I'm going to explain this paper to you, DISN, Deep Implicit Surface Network for High Quality Single View 3D Reconstruction. The purpose of this study is to create a 3D shape that represents the object's overall structure as well as fine-grained features. In recent years, so many single view 3D reconstruction algorithms have been presented, with deep learning based systems achieving particularly promising results. Many of these algorithms use voxels or point clouds to represent 3D shapes because they are easier to encode in a neural network. But the resolution of such representations is frequently limited. A few recent methods have looked into using explicit surface representations in a neural network, but they all assume a fixed topology which limits their adaptability. Furthermore, training losses in point and mesh based approaches are chamfer distance and earth mover distance. These distances are simply approximations for measuring shape similarity. In this paper, the author proposes an alternative implicit 3D surface representation, sign distance functions (SDF), to overcome the existing drawbacks in voxels, point clouds, and meshes. SDF is a continuous function that maps a given spatial point to a real value. In this paper, the author introduces an efficient, flexible, and effective deep implicit surface network, which is a feed-forward deep neural network to predict the SDF from an input image. The SDF value for any given point is predicted by deep implicit surface network using a single image as input. Unlike 3D CNN algorithms, which build a volumetric grid with fixed resolution, deep implicit surface network generates a continuous field with flexible resolution. Let's understand the architecture of the deep implicit surface network. Camera posture estimation and SDF prediction are two components of the implicit surface network. In camera pose estimation, the purpose is to estimate the relevant viewpoint from an input image. The network is trained by using the ShapeNet core dataset where all the models are aligned. As a result, they assume a fixed set of unique parameters and use this aligned model space as the world space. As mentioned in another paper, explicitly regressing camera parameters from an input image using a convolutional neural network frequently fails to create appropriate postures. Another author proposes a simplified aggregate strategy for regressing camera position by aggregating numerous candidate poses. This strategy, however, requires a huge number of network parameters as well as a lengthy training phase. In this paper, the author shows a network that is more efficient and effective using the previous paper where they demonstrated that a 6D rotation representation is continuous and easier to regress for a neural network than more typically used representations like quaternions and Euler angles. The author applies the expected camera posture to translate a given point cloud from world space to camera coordinate space. Instead of calculating losses on camera parameters directly, the author uses the predicted camera pose to transform a given point cloud from the world space to the camera coordinate space. The mean squared error between the converted point cloud and the ground truth point cloud in camera space is used to calculate the loss of camera. In SDF prediction with deep neural network, the proposed network's purpose is to calculate SDF. Unlike prior reconstruction methods that relied on approximated chamfer distance and earth mover distance losses, the proposed guidance is based on genuine ground truth. As proposed in the earlier paper, deep SDF is a direct technique for regressing SDF with a neural network. But the author notices convergence issues in early trials when they use a similar network topology in a feed-forward approach. The proposed approach is to map the given point position to a higher dimensional feature space using a multilayer perceptron. The SDF value is then regressed using this high dimensional feature, which is concatenated with global and local image features respectively. In local feature extraction, when only global picture characteristics are used, it is difficult to capture shape details such as holes and thin structures as initial trials revealed. However, such outcomes can be visually unsatisfactory. Instead of constructing a binary classification problem, for example inside or outside of a shape, the author regresses continuous SDF values. The method can be used to extract surfaces that correspond to distinct ISO values. The author proposes a weighted loss function to ensure that the network focuses on recovering details near and inside the ISO surface. For surface reconstruction, to create a mesh surface, the author starts by creating a dense 3D grid and estimating SDF values for each grid point. Then they used marking cubes to construct the 3D mesh that corresponds to the ISO surface after computing the SDF values for each point in the dense grid. In the experiments part, a quantitative and qualitative comparison of the proposed single view reconstruction approach is performed with the state-of-the-art methods like AtlasNet, Pixel2Mesh, 3DN, OCCNet, IMNet, etc. Deep Implicit Surface Network is the first deep learning model that can capture such high quality details from single view photos. For the evaluation matrix, to compute the difference between a reconstructed mesh object and its ground truth mesh, they use four commonly used metrics. Number 1, chamfer distance. Second, earth movers distance between uniformly sampled point clouds. Third, intersection over union on voxelized meshes. And fourth is F-score. Testing of the proposed method is done on a variety of shape categories utilizing both synthetic data derived from 3D shape datasets and online product photos. Multiple 2D views of the same object can also be fed into the proposed model. They use max pooling and use the generated features as input to each decoder after extracting the global and local image features for each view. Deep Implicit Surface Network can better handle shape details by combining multi-view characteristics. The proposed approach can only handle objects with a clear background because it is trained using rendered images. To overcome this issue, their future work includes enhancing sign distance function creation with texture prediction using a differentiable renderer in the future. Thank you.